go ahead and evaluate rational exponents. And most of the time, that's going to be most easily done by using the root first and then the power. At least if we're going to get an integer result, the root first and then the power will be easier. So if we have 27 to the 2/3, that's the third root of 27 to the second power. The third root of 27 is 3, so that's just 3 squared, which is 9. If we have 4 to the negative 3/2, that's the square root of 4 to the negative 3. The square root of 4 is 2, so we'll have 2 to the negative 3. That's 1 over 2 to the third, which 2 to the third works out to 8. Negative 32 to the power 4/5, that's going to be the fifth root of negative 32 to the fourth. Fifth root of negative 32 is negative 2. So we have negative 2 to the fourth. That's positive 16. Negative 8 to the power negative 1/3. That's the third root of negative 8 to the power negative 1. So that's negative 2 to the power negative 1, which is 1 over negative 2 to the power 1. In other words, 1 over negative 2, which we would normally write as negative 1/2. Now something weird happens with this last one. We'll have the fourth root of negative 81 to the third, but we can't take an even root of a negative number. So this is undefined. So this is what happens when we evaluate a rational exponent where the result turns out to be rational, where we can actually take the roots. If the root involved is irrational, we'll use the second way of writing our rational exponent in terms of radicals to write an expression without exponents. So we have 2 to the 2/3. We could say that that's going to be the third root of 2 squared. But because the third root of 2 is irrational, right? 2 doesn't have a nice third root. We would rather say that that's going to be the third root of 2 squared. That is the third root of 4. Now 4 doesn't have any perfect third power factors, so we can't simplify that radical any further. 5 to the negative 1/2, that's going to be the square root of 5 to the negative 1. And I think that in this case, I'm happy with writing that as 1 over the square root of 5. But I'm told to rationalize any denominators. So I think I'm going to have 1 over the square root of 5, multiply my denominator and my numerator both by the square root of 5. And I'll have square root of 5 over square root 25, which is the square root of 5 over 5. Okay, next I have 8 to the power 4/5. And I'd like to be able to say take the fifth root of 8 and raise that to the fourth power. But I can't because 8 doesn't have a nice fifth root. So instead I'm going to say take the fifth root of 8 to the fourth. The bad news is I'm now taking the fifth root of 4096. However, the good news is I can use my calculator to go through the perfect fifth powers, and I can discover that 4096 is 1024 times 4. So I can split up this fifth root as 1024, the fifth root, times the fifth root of 4. And I can actually do the fifth root of 1024. That's just 4. And so this simplifies as 4 times the fifth root of 4. Not as bad as it looks. Finally, negative 4 to the power negative 2/3. I could say that this is the third root of negative 4, all to the negative 2 power. But negative 4 doesn't have a nice third root. It does have a third root, right? It's some negative number, but it's not a nice one. So I can say, well, this is the third root of negative 4 to the power negative 2. So the third root of 1 over negative 4 squared. The third root of 1 over 16. Now I can play rationalizing games and say this is the third root of 1 over the third root of 16. 1 over the third root of 16. Going through, I discover that 16 is a factor of 64. If I multiply my numerator and denominator by the third root of 4, I'll get the third root of 4 over the third root of 64, or the third root of 4 over 4. And that's that last root fully simplified with the denominator rationalized.